Okay, we're jumping to the other side of the main breaker, and we're going to talk about supply side connections. 705.11 and 230.82.6 cover supply side connections, and 230.82 specifically says, yeah, you can connect PV, wind, energy storage systems, other interconnected power production sources on the supply side of the main service disconnecting means. So let's take a look at our diagram, quick review. We've got our primary power source coming in, connected to this AC main service panel. There's our main service disconnecting means, main breaker, and we are interconnecting between that and the meter. There's our connection over to our PV system or whatever is supplying that particular inverter. Okay, so that's a supply side connection. Now, 230.82.6 does require that the disconnecting means be listed as suitable for service equipment. Typically, what that means is that you are able to bond a grounded conductor to ground in that piece of equipment, so connect neutral and ground. And we'll talk about grounding requirements a little later. These are also required to have overcurrent protection in accordance with Article 230, Part 7, which is the overcurrent protection for services section there. So 705.11a, supply side system size. And often we do a supply side connection because, as we saw talking about load side connections, the bus bars often limit how much we can put on those systems. And significant limits. For a 200 amp typical residential service, if we're looking at that, we have 32 amps of IMAX we can connect. That's going to be, 7,500 watt inverter, or give or take. You can do the math. So that's a size limit. When we move to the supply side of that main disconnect, we are able to interconnect much larger systems because we're not worried about that bus bar. All that needs to be able to handle the second source of power are those existing service conductors that are already there, right? So we're not worried about the bus bar anymore, and we're allowed to size the power source continuous output current rating, that's IMAX, up to the service conductor ampacity. So IMAX, not times 1.25, just IMAX has to be less than or equal to the service conductor ampacity. Now, that's important to keep in mind because a lot of times it can be easy to confuse, well, what's the real size of this thing? I've got a 200 amp main breaker in this diagram here. Well, a lot of times that doesn't really mean that you have 200 amp rated conductors coming in. It depends on what your utility uses. And so we want to make sure that we're looking at the conductor size itself. It may mean contacting the utility to see what they rate those conductors as or what size they are using. Maybe you're able to identify that. But it's not just say, 200 amp main breaker, 200 amps of PV. It could be as long as the conductors are 200 amps. So we're showing in this example that very case. We've got a 200 amp IMAX up to 200 amps connected there. But there should be really an asterisk there. It's really going to be limited by whatever those service conductors, whatever size they are. Because conceivably, if there's no load, everything's going back to the primary power source, well, those wires are going to have to be able to handle it. Now, there's a caveat here. Unless controlled by a power control system, and I bet you can figure out what that does. It's a system that controls power. We'll talk about that in 705.13 in just a little bit. So an example, as I said already, a little simplistic, 200 amps existing service, up to 200 amp total IMAX. Again, really paying attention to the conductors and their ampacity. What about those supply side conductors? Well, we're talking here now from the point of interconnection to the first overcurrent protection device. So not the service conductors, the supply side conductors. So if we back up just briefly, we would be saying from here to there, the point of connection to the first overcurrent protection device. Okay, so those conductors. We size them following the rules in 705.28, those are going to be pretty much the same as sizing inverter output circuit conductors as in Article 690, and we address conductor sizing elsewhere in the course. There is, however, a bare minimum. They've got to be at least 6 AWG copper, 4 AWG aluminum, or bigger. Can't be any smaller than that. Even if it's a pretty small system and we don't really need that size of wire, That's the absolute minimum size that we can use for that length of wire. And it makes sense to some degree because, those wires are fundamentally exposed to full fault current from the grid, whatever that primary power source is, up to that first overcurrent protection device. So we want to make sure that we have that minimum capability to them. We have to follow the rules in 230.30 and 230.43. These are wiring methods and conduit types for underground service conductors, 230.30, or service entrance conductors entering the building, 230.43. There's some specifics in there that we want to pay attention to. May not be a big deal if you are, for instance, just doing this on the exterior of a building where there's the main service there and we're connecting into it all on the outside, but there are specific installation requirements to pay attention to based on the specific method that you're using. Okay, that overcurrent protection, right? We just talked about the conductors from the point of interconnection up to the overcurrent protection. Well, 705.11c covers supply side overcurrent protection. We're going to size it in accordance with 705.30. And again, this is very similar to the way we do it for inverter circuits in Article 690. Not a whole lot of differences here, really, so we'll cover that elsewhere in the course. The disconnect itself has to be on the service side of non-integral fuses. So what this really means is we want to have the disconnect so that it isolates the fuses from the primary power source when the disconnect is off. Right? I don't want the fuses always connected to the grid if the switch is off, because then, well, how do I change those fuses? My power source is always energized. So throwing the disconnect here should isolate the fuses from the primary power source. In most cases, that's going to cause the inverter and that system to shut off anyway. Fuses are de-energized. Now we can safely work on them if needed. If those fuses are integral, well, they're going to be built into a box that's already set up that way, right? The image on the slide here shows that primary power source on top. When the switch is open, it isolates the fuses from that primary power source. That's just the way it's built. If you have a switch that's separate from a box with fuses in it, then you have to set it up so that also is true. The overcurrent protection device location is also going to be specified based on whether we're making a connection inside or outside the building. Again, remember, we've got full utility fault current available here, so we really want to make sure that we're not overextending these conductors and possibly creating a hazard as a result. So outside the building, we have to have these overcurrent protection devices at a readily accessible location outside or right at the very first point where the conductors enter the building. Right, so they come in the building and right on the other side of the wall, that's where the overcurrent protection device is. So the fuse disconnect switch is very common, or maybe it's a panel with a breaker in it. Whatever that overcurrent protection device is, it's right there on the other side of the wall. So we don't have a long run of unprotected conductor length. Now, if we do make the connection inside the building, then we have limits on how long those conductors can be. So if these are inside the building in a dwelling unit, 10 feet of conductor length, not of they're 10 feet apart, these two boxes, conductor length, right? Look at the box on the slide. There's 1.5 feet of conductor inside of there. Okay, so conductor length from point to point until we get to that overcurrent protection device, 10 feet inside a dwelling unit, otherwise up to 16.5 feet in non-dwelling units. Now, there's also an allowance that only applies to non-dwelling units. This is if we have cable limiters within 16.5 feet of that point of connection. So we have cable limiters which prevent overload on the conductors that they are protecting, not overcurrent necessarily, but overload. Then we can run up to 71 feet of conductor length. So we're providing additional protection through the cable limiters, allows us to extend that length further. But again, this only applies in non-dwelling units. And this length, again, is from the point of connection to the first overcurrent protection device. Okay, so inside or outside a building, and then inside we have the length requirements that differ for dwelling units and non-dwelling units. Okay, a big question is always, how do you actually physically make the supply side connection? In some residential equipment, you can't. There's no way to do it. There's insulated flat bus bars that you're not allowed to tap into. There's nowhere to double lug or terminate or anything, and you just can't do it. Other equipment, there's a lot of options. in commercial applications. Sometimes it can be much easier. Sometimes it can still be different. Here on the slide are some examples, and your mileage may vary on these. Your jurisdiction or utility may have specific requirements. The equipment they're using, that you're using, may or may not be suitable for use with these, or they may not have a listed product that works together with it. So this is where some of the difficulty can come in when we're making the supply side connection. A common method is to use a Polaris or other type of insulated connector. Right, we've got a wire, we cut the wire, it takes up 2 of the holes, the new wire takes up the 3rd hole in the insulated connector. There'd be 1 per phase and probably the grounded conductor as well. So that's one way of doing it. Now these things are big and bulky, and we need to take that into account. They're going to take up a bunch of space wherever they end up. And, that's something that we need to consider, of course. The Milbank load tap connector. This works obviously with a certain brand of equipment, and this looks like it's set up to allow us to double lug. This connects to the bottom of a meter base, and then it gives you a point to connect another conductor. Bottom of a meter base. You might not be allowed to go in there, so you might not be able to use this option. You might not have this kind of equipment there, so it might not be listed for use with the meter base that you have. Again, it takes some work and investigation to figure out how you're going to do this. Over here on the right would be an example of, presumably, manufacturer-approved connections to existing equipment. We're going to certainly want to talk to them and make sure it's okay, but we've got our supply-side conductors connected to the primary power source here. Again, these have to be at least 6 AWG copper, 4 AWG aluminum. This is a good image that shows you, hey, disconnect open, fuses isolated from the primary power source. We're connected on the supply side of that main service. Disconnecting means in this case, it's not a breaker. It is a fused switch. So again, we'll have to make sure that it's okay to do this. Especially if we would be tapping new holes here that we might connect to if there wasn't already a spot to do it. Again, that requires working with the manufacturer to verify that you're not modifying the equipment in a way that's going to violate its listing, opening you to liability, possibly through equipment failure. Another really popular way of making this connection in the bottom middle, insulation piercing connectors. This is made to go over the service conductor and in the other half. So the service conductor would be running through one side of it here. Your new wire would lay in here and connect to it. You tighten this down, the teeth pierce through the conductor insulation and then make the electrical connection between the two. Of course, they have to be sized correctly for the right size wire and maybe 2 different sizes. It all depends. We need the right one to do the job. Again, these are going to take up some space in whatever enclosure they're installed in. Another option that some people are having a lot of success with in jurisdictions that allow it would be the connector meter base collar. So this basically, this would be connected where your existing meter was, and then your existing meter goes on the outside of it. So I'm connecting between the meter and the rest of the equipment, and then this gives me a place to wire in the PV system. Here's the wiring terminals down there. There's a built-in overcurrent protection device, so it's really well engineered to meet the requirements for how we can do this. But of course, as you can imagine, this, even though it's a listed product, is going to require your jurisdiction and your utility to accept it as a means for making the supply side connection. Some utilities do, some don't, some have never heard of them, and maybe they will if you can educate them about it. But really, that's going to be the case for all of this stuff. We really want to think through what the possibilities are based on the existing equipment, what the options for listed equipment is, and make sure that these things are going to be compatible. Here's a good example of those insulation piercing connectors. You can see the service conductors coming in. There's our supply side conductors. There's the insulation piercing connector on each of the 2 phases in a residential application. So 705.11d and 230.46 connections to those service conductors, as is shown here. Meter sockets and equipment under utility control. Hey, you can only make connections in there if the utility allows it. They got a little kind of lock, or it's sort of wired shut. You can't just clip that in and go in there and stick on double lugs on the meter base or whatever it may be. You have to make sure with them if you want to do this inside a part of the equipment that they control, and you know what it is, if you go up to service, you can see where you're kept out of by the various means they use. It's not, you can definitely get in there if you want to, but you're not supposed to. And it's also very dangerous. And if you make a connection in there that they don't allow, you're not going to pass an inspection and be allowed to operate the system. So you got to follow their rules. We've got to use listed connectors to do this. All right, so we're going to follow 110.14 for that. We're going to comply with the enclosure fill requirements. I kind of hit on this a little bit already. Especially Polaris connectors on a 3-phase service with big conductors, they can really take up some space in a hurry. Along with our new wires, we need to make sure we're not overfilling that enclosure and causing overheating as a result. Now, 230.46 specifically deals with splicing and tapping to service entrance conductors, and it says, hey, they've got to be listed, those devices that we use. It also specifically says that, hey, power distribution blocks must be marked as suitable for use on the line side, or some kind of equivalent wording that means that. There's also a provision in the 2020 National Electrical Code that says, hey, as of January 1, 2023, anything else you're using pretty much has to have that same language on it as well. Splice devices, pressure connectors, those also have to be marked for suitable for use on the line side. So presumably that is a listing and a testing requirement, and this is actually a new addition to the 2020 NEC. So look for those products to come out or be relisted or updated to meet these requirements. If you adopt the 2020 NEC and it's before January 1st, 2023, this doesn't apply to splice devices and pressure connectors. Once we hit that date, whenever you adopt, then this will be a requirement. So, don't stock up on a lot of this stuff in advance of then, if you're doing supply side connections, if it doesn't have this marking on it. Any modifications, as I already mentioned, have to really coordinate with the manufacturer, make sure that you're not violating the listing, or there's always the option to get it evaluated and labeled in the field. Right, so we get it engineered, we say we can do these modifications to this equipment, we call in an NRTL, they come out and look at the system, do some testing, evaluate it, sign off on it, and field label it as, okay, this equipment is good to go. Obviously, going to take some extra work, and that's a more expensive option, but in some cases, that's all you can do based on the existing equipment and trying to interconnect to it. What about grounding systems connected on the supply side? This has been a big topic over the years in the industry, and this applies when we're installing the connection in a separate enclosure from the service equipment. If we're just connecting in the service equipment, it doesn't really matter. If we are running conductors from that point of interconnection to another enclosure where we're going to have our overcurrent protection devices and disconnecting means, then we've got to follow these rules in 250.25. So this is in 250, Article 250 on grounding. It's not in Article 705, where the other supply side requirements that we've been talking about thus far are all located. So it depends on what the utility supply system is. Is it grounded or is it not grounded? So grounded, more common, right? 120/240 split phase, grounded. 208 120 3-phase, grounded. 277 480 3-phase, grounded. A lot of systems are grounded, but there are some delta and Y configurations that are not. The grounding requirements for the supply side connection system depend on what that utility system is. So obviously you need to figure out what that is. It might be very easy. It's somebody's house. I know it's 120/240. It's got a neutral conductor. It's a grounded supply. 250.25a says, hey, if it's grounded, go look at 250.24a through D. And what that basically says is you need to bring a grounded conductor to each of the disconnecting means. So I need to run the neutral from the point of interconnection to that disconnecting means for the supply side connected system. We need to run a grounding electrode conductor from that grounded conductor and the equipment grounding conductor and the enclosure, right? All that stuff's bonded together. The neutral, the enclosure of the switch itself, the equipment grounding conductors all come to that point. And then from there, we run to the grounding electrode using a grounding electrode conductor. So we're basically, again, have an AC system bond, a main bonding jumper on the AC side that's connecting neutral to ground, Everything on the equipment grounding system is coming together, and we're running a grounding electrode conductor to the grounding electrode system. If we have an ungrounded utility supply system, so no neutral, we've got an ungrounded delta or Y configuration, then we have to comply with 250.24e. And what that says is, hey, grounding electrode conductor connects from the grounding electrode to the metal enclosure of the service conductors somewhere between the load end of the meter and the service disconnect. So somewhere along the way, I need to connect the grounding electrode conductor to that enclosure of the service disconnect. So the supply side system disconnect, we'll say, right? Of course, that metal enclosure is also going to be bonded to all the equipment grounding conductors that are over on the supply side system. They're all coming together, and then we're running at the ground. It's basically saying, hey, there's no neutral with the utility. You don't need to run a neutral to the supply side system because there isn't one anyway. You still got to have a grounding electrode conductor connected to the grounding electrode system, but it's just connecting the chassis of this switch plus the equipment grounding system all together. Hey, there's no neutral to deal with. Pretty straightforward. Probably more straightforward to look at a picture, right? And this is our more common example of grounding a system where we have a grounded primary power source. So you can see we've got line 1 and line 2 coming in from the grid. We've got our neutral conductor here. We've got our ground connection, our mean bonding jumper over to ground. There's our grounding electrode. So primary power source is grounded. 250.24a says that we need to run that grounded conductor. So the neutral has to go to the disconnect for the supply side connected system. That's our PV system disconnect in this case. And we've got to have the bonding jumper. That bonding jumper is connecting the grounded conductor to ground. It's also at that ground terminal, we've got our equipment grounding conductor coming in from our AC circuit. And of course, assuming this is a metallic enclosure, we're going to have a connection from the grounding terminal to the chassis of that switch itself. So neutral connected, equipment grounding connected, chassis of switch connected, and then we run a grounding electrode conductor to the grounding electrode system, whatever that may be. Rod, pipe, plate, UFR, however many there are bonded together to form that system. So it's pretty simple. It's really kind of duplicating what's happening in that main AC service panel, right? If you look over there, we've got our connection to between the ground and conductor and ground. All of this stuff is bonded to this bus bar. All of the branch circuits are going to have equipment grounding conductors coming in here. And then we've got a grounding electrode conductor connected to the electrode itself. So it's really just kind of doing the same thing at the point where we have our disconnect and overcurrent protection for the supply side connected system. Now, there's always a question, what about that neutral? Do I really need it? Because a lot of inverters don't. A lot of inverters do not require a neutral conductor. You got to talk to the manufacturer, though. In my experience, a lot of 240 volt ones often do, just because it's not a huge cost. So they're like, whatever. But a lot of them don't really need it. And a lot of larger inverters definitely don't need it. You need to consult the instructions for the equipment you're using. Talk to the manufacturer if you need to. They may say, hey, yeah, there's no need. This thing, you're just wasting wire. And in which case, you don't need to run it. But even if the inverter doesn't need it, you still need to run it to that PV system disconnect for the supply side connected system. Okay, up next, we'll have a quick discussion on where to connect with all these options we've just gone over, and I'll see you there soon.